Okay, so today I'm going to introduce to you what gas laws are. There's several of them. At first, they might seem like there's random things that we found, and kind of that's exactly what happened. We found that there were certain things or patterns within the way that gases behaved, and then we mathematically linked those things. So before I begin, I want to talk about the four basic properties that gases have, and that is pressure. So this is basically defined as how often gases or molecules hit the sides of the container. That's what pressure kind of really is. Volume, how much space they occupy. These are usually given in liters. Moles, how many of something you have. How much of whatever it is that occupies that space do you have? And finally, temperature. Now, let me go ahead and say one of the biggest issues that I see is that people do not turn these into Kelvin. Truth be known, I think that most gas laws people consider an easier topic, but you got to know certain rules, and one of those is you got to turn temperature into Kelvin. And so there are times that maybe you don't have to, just do it. It gets you into the right pattern. Okay, so let me introduce to you some of the individual gas laws that we figured out early on, and then show you how we incorporate all those into one. Because truth be known, I don't want you to have to memorize these one by one. I want you to know one equation and then use it to your advantage, okay? So, first of all, let's start with Gay-Lussac's law, or Gay-Lussac's law. And what he said here is that pressure of an amount of gas, whatever amount that is directly proportional to temperature if volume is constant. So that also means that your number of moles of that gas is constant. So we could say that pressure is directly proportional to temperature. Or to put that in mathematical terms, we could say that P is equal to T times some constant. That's all that really means. Then Charles' law states that the volume of a gas is directly proportional to temperature when pressure is constant. So now we keep pressure the same, and we say that volume is directly proportional to temperature. In other words, we could say V is equal to T times some other constant. I'm assuming these constants are different at this point. Next, we have Boyle's law. Here, he says that the volume of the amount of gas at a constant temperature is inversely proportional to pressure. Now remember, inversely proportional means we got a 1 over. So that means that P is proportional to 1 divided by V. Or you can say that P times V is equal to some constant. So when one goes up, the other one goes down, right? As pressure goes up, volume is going to go down, or volume goes down, pressure goes up. Next, we have Avogadro's law. Here he says that the volume and number of moles of a gas are directly proportional if pressure and temperature are constant. So we ignore pressure and temperature, and we simply say that the volume and number of moles are proportional, or V is equal to moles times some unknown constant. Well, all of these went to really lead to one rule, and that is the ideal gas law. And there we go. Now, before I go further, let me just tell you that P is pressure, V is volume, N is moles, just like we talked about, temperature is in Kelvin, just like we talked about, and R becomes the gas constant. There are different versions of this constant, so you have to make sure that whatever units you are using over here actually cancel out. So in other words, that you're using the volume of liters, you're using the pressure of ATMs, we're using moles, and we're using Kelvin. So that's another way that you can sort of check yourself that you're in the right units. So a lot of times with gas laws, what we do is we compare the state of one gas law, or one condition that gases are under, and we change that condition to something else. And when we change that condition to something else, we sometimes need to know what are the variables and what they change to. So we can say, we can derive things from this ideal gas law. And that's the reason why I say that's the one that you really need to know. If I divide each side here by nRT, we can see that PV equals nRT, or PV over nRT is equal to 1, excuse me. So that allows us to compare one set of gas conditions to another set of gas conditions. So we could say that P1V1 over N1R1T1 is equal to P2V2 over N2R2T2. That kind of sounds like something from sci-fi. But in reality here, realize that the R's are the same and they will cancel out. And that's where we get this type of relationship. This is something that you can derive because all you need to know is PV equals nRT, and you can mathematically figure out what this is, hopefully. And then when you get to problems, you often see that people will say, this and this change. Or they point out that this and this have changed. And so you can use that information to solve for what you need. And you just assume that the things that aren't mentioned or the things that are told to you that they're constant, that means that they don't change. And that means it's just like R and you cancel them out of each side of their equation. So I'll give you examples of each of those in the next video. So make sure you do check that out. But that's basically all these reactions or all of these problems are really doing is going through these types of things. It is important to note, sometimes you'll hear things about standard temperature and pressure, or STP. What that means is the temperature is at 0 degrees Celsius, which is 273.15 Kelvin. Pressure's at 1 atm. And at this pressure and temperature, that means 1 mole of gas is about 22.4 liters. It's pretty big. Now, one of the things that we say there is that gas molecules are so far apart, it doesn't necessarily make a difference as to what size they are. That's an assumption we use in this process, so that is something to keep in mind as well. Common mistakes in these problems: number one, make sure, as I said, you keep your temperature in Kelvin, and then also make sure that you're using the correct R value. So I'll go through some problems in just a minute on the next video. See you there.